One is some sort of basic dynamics of so-called asymptotically holomorphic maps. I'll define what I mean by them. And especially those which are polynomial-like in nature. And the subject is really meant to be, the study is to be used in the study of renormalization of one-dimensional dynamical systems, more specifically classes of unimodal maps. Okay, so this is something that This is something I actually worked quite a bit with Wellington and Alberto Pinto, also from Portugal. So we studied renormalization of unimodal maps with a finite degree of smoothness, right? So I'll get to that motivation a little bit later. But let me first right away tell you what these asymptotically holomorphic maps are and what are the polynomial-like versions of these maps. So suppose you have a map from an open subset of the complex plane or the Riemann sphere. It's a continuous map into the Riemann sphere or into the complex plane. And suppose you have some compact invariant subset for this map, and you're given some number r greater than 1. So you say that F is asymptotically holomorphic of order R near the set if, well, first of all, the map has to be CR. It has to be quasi-regular. By quasi-regular, I mean that locally it's like the composition of a quasi-conformal homeomorphism or diffeomorphism with a holomorphic map, okay? Well, with a holomorphic branch covering map, so. And the property that defines what it means to be asymptotically holomorphic is the property that the dilatation of the map should vanish with a certain order, in this case order r minus 1, as you get closer and closer to the invariant set, okay? So I just want to remind you that the dilatation is just the ratio of the dilatation at a point is the ratio of the d bar derivative of the map at that point by the d derivative, okay? So, so what is an asymptotically holomorphic polynomial-like map? Okay, I'm going to be referring to the from now on. I'm going to use the acronym AHPL. Okay, because it's a mouthful to say, right? Asymptotically holomorphic polynomial-like map. So anyway, so what is the definition? Definition is topologically these maps should be like a polynomial-like map, a standard polynomial-like map. So you have two disks. One compactly contained in the other, and you have a map from the smaller disk to the larger disk, which is onto. It's a proper map, okay? So pre-images of compact sets have to be compact. So with that in mind, you can consider the so-called filled-in Julia set of the map is just the intersection of these pre-images of V. Because the map is proper, this is actually a compact set. So this is called the filled-in Julia set. And I'm looking at some forward invariant subset of the filled-in Julia set. And the map has to be, so it is an AHPL map if the following things happen. So it has to be a degree D branch covering map of U onto V, branched at a unique critical point. So we are talking only about unicritical maps, okay? And it has to be asymptotically holomorphic near the set lambda. So here's a picture. Well, and by the way, I required lambda to contain the critical point. Where is this? Right here, somewhere. Yeah, right here. And therefore, because the set is forward invariant, this set actually contains the entire post-critical set. So, so here's a picture. So you have two Jordan domains, U and V. The map maps U onto V. There is this funny, Julia set. In this case, I drew it with no interior components. I mean, the filled-in Julia set. And there is some subset. In this case, is this blue set that you see here. It's lambda, which is supposed to be forward invariant. And it contains the critical point of the map, the unique critical point that the map has. And if you take a point in the domain and you look at its distance to lambda, then the dilatation of the map at this point has to be of the order this distance raised to the power r minus 1. Okay? So we're going to be mostly interested in the case where lambda actually sits in the real axis. The map is symmetric about the real axis, and lambda is in the real axis. And then it's not difficult to see that if you have a CR map on the real line, it always admits some kind of an asymptotically holomorphic extension to a neighborhood of the real line. But it's obviously not always the case that it will be polynomial-like in this with this structure, right? Okay, so these maps, these asymptotically holomorphic maps, not AHPL maps, but asymptotically holomorphic maps, they have appeared, a few times in the literature already. There was work by, I think by Lyubich himself, by Grajcik, Sands, and Swiatek, and also in the thesis of Pablo Guarino. He's used these maps quite a bit. Okay. In fact, there's a reference here at the end. So, okay. So what is good about these maps is that they can be written as a composition of a quasi-conformal diffeomorphism with a holomorphic branch covering map. Okay, you can write it. So you can write it this way: phi composed with G. There is also a way of decomposing it in the opposite way. You write G, some other G composed with some other phi. Okay. These things are kind of, you can intertwine them. So G is a holomorphic branch covering from U to V, and phi is a holomorphic, an asymptotically holomorphic diffeomorphism. I wrote here homeomorphism, but in general we are going to only care about maps which are at least C3. So this phi will actually be a C2 diffeomorphism. Okay, at least a C2 diffeomorphism. So anyway, or actually to be a C3 diffeomorphism, but asymptotically holomorphic of order 3, so it means that the dilatation goes quadratically to 0 as you get closer to lambda. So I would like to warn you that these maps are definitely not uniformly quasi-regular. They're quasi-regular maps, but if you iterate, the dilatation starts to grow, can get very bad. And for this reason, these maps are not quasi-conformally conjugate to actual polynomials. If a map is uniformly quasi-regular, then there's a very kind of old means, goes back to Douadian, Hubbard, and Sullivan. There's a way of taking the iterates of the map and you kind of average the quasi-conformal dilatation along the orbits by a bare center construction. And what you get is some invariant Beltrami differential that you can integrate. You get some quasi-conformal homeomorphism that conjugates the map to an actual polynomial-like map, to an actual holomorphic map. So this is not the case here. These maps are definitely not uniformly, they're not uniformly quasi-regular, and they are not also, they are not uniformly asymptotically conformal. There's a little theory worked out by Gardner and Sullivan, which deals with maps that have the property that they are quasi-regular, but when you iterate along backward branches, you get some kind of uniform control of the distortion. Okay, so these maps are called uniformly asymptotically conformal, and this is also definitely not the case here. Okay, so we need other techniques to study these maps. But the question is, why should we bother? Why should we study these maps? So let me just say just a couple of words about this. So first is that, as you saw in Arthur's talk, there's this beautiful theory of renormalization of real analytic quadratic-like or polynomial-like unimodal maps, and also of quadratic-like germs or polynomial-like germs in the complex plane. So this is a theory that started with Sullivan and Douadian and Hubbard, and it was progressively enhanced by several beautiful results by McMullen, by Lyubich, by Arthur himself and Lyubich. And I put some 3 points here because there are many other contributions. There are contributions by Sebastian himself, by Levin, by a lot of people. Yeah. So I'm here just sort of mentioning it. And at the same time, not the same time, but shortly after Lyubich's work, Wellington, Alberto, and we worked on a theory of renormalization of smooth smooth maps, unimodal maps with a finite degree of smoothness, okay? So this was also mentioned by Arthur in his talk. But unfortunately, the techniques are kind of a bit ugly. There's, it's very, heavy nonlinear analysis. It's not very, it's not pretty, okay? It's unlike this city, which is very beautiful. What? Yeah, well, but analysis can be very beautiful too, I love analysis, I don't know. So this was actually using some methods from nonlinear functional analysis that were initiated by this guy Davey, who's actually not really in dynamics, he's an analyst, right? So anyway, so the motivation for our study is to try to develop a more direct approach using these asymptotically holomorphic maps to kind of do away with this somehow, maybe, I don't know, and try to do a proof of renormalization hyperbolicity or convergence at least using methods which are more similar, in nature to the methods used here. Okay, so so you think, well, okay, let's try to use these maps, and then you realize that there's some very basic questions about these maps that you don't know how to answer right away. So there's some very basic questions that can be asked, which are similar to questions you ask about standard polynomial-like maps, which are kind of easy to answer in the holomorphic case. So, for instance, basic question number one is: are the expanding periodic orbits dense in the Julia set of these maps? The Julia set here is defined as the boundary of the filled-in Julia set. Okay. Yeah. Well, I define the field. I define the filled-in Julia set in a very easy set theoretic way by taking pre-images of V and intersecting them all. Right. This is by definition the filled-in Julia set here. So the Julia set is the boundary of the set, and you might ask, are the periodic points dense? Now, in the polynomial-like case, this can be answered right away in several ways. One of the ways is just to notice that there is this theorem of Duadie and Hubbard that says that such maps in the holomorphic case are always conjugate to polynomials. They're quasi-conformally conjugate to polynomials. And for polynomials are rational maps, and for rational maps it's well known that the Julia set is precisely the closure of the expanding periodic orbits, right? So, but here we don't have a straightening theorem like Duadie and Hubbard, okay? Another question is, when is the Julia set locally connected? Okay? Well, this is actually not an easy question, even in the holomorphic case. There's sometimes it is, sometimes it isn't, and deciding when is a serious problem. So another thing is, what is the classification of the components of the interior of the filled-in Julia set, right? The stable components. So in the case of bona fide polynomial-like maps, you can use Sullivan's classification for rational maps, because again, these maps are, they can be, you can glue something like z go to z squared to the outside, you get a polynomial up to quasi-conformal conjugacy, and then you can apply for the polynomial, you can apply what you know, so you know how to classify, that, sometimes you might have Ziegel disks or whatever, but you definitely don't have Hermann rings because these maps are conjugate to polynomials. But here, you don't know any of these things, at least not in principle. So another thing is, can F have wandering domains? Again, if you knew that the map was uniformly quasi-regular, you could conjugate it to a polynomial, and that's it. And you apply Sullivan's no wandering domains theorem, you deduce that there are no wandering domains, but you don't have that. And finally, is there a kind of a topological pullback argument? So for those who don't know, when you have two polynomial-like maps which have the same topology on the real axis, and let's assume that actually the dynamics on the real axis are quasi symmetrically conjugate, which is something you can actually prove, then just from that you deduce that there is a quasi-conformal conjugacy between the two maps by a kind of a pullback construction. But here the pullback cannot be done either, because as you start pulling back, the dilatation of the lifted maps becomes worse and worse and worse, so you can't really take a limit. And by the way, if you were able to say yes to this question, these 4 previous questions, they all follow right away. I mean, or at least, well, not this one. This one needs extra hypothesis. Anyway, so like I said, these questions are not really obvious to answer in general, but, and this is the point of our work so far, is that when F happens to be a map which is symmetric about the real axis, and when restricted to the real axis, it is a unimodal map of which is infinitely renormalizable of bounded type, then we can answer these questions. And this is the contents of our main theorem. So here's the main theorem. So suppose you have a unimodal map first, so just on the interval, which is at least C3 plus something, okay? And it's unimodal, infinitely renormalizable. I'll explain what this means in a moment. Of bounded type, has a unique critical point. It has to have even criticality because the map has to be unimodal on the real line. So then what can you say? That you can say that every extension of this map to a neighborhood of the interval in the complex plane, which happens to be asymptotically holomorphic with the same degree of smoothness as F itself, right? So I call it capital F right here. So every such map, every such extension will have the property that as you renormalize, it will, in some sense, it will become one of these AHPL-maps, okay? If you wait long enough, I didn't say it here, this is not for every n, but it has to be only for sufficiently large n, okay? So you have these domains containing the critical point and certain iterates with the following properties. Well, the iterate of the map restricted to these domains, they map the smaller domain into the larger domain, has a asymptotically polynomial-like map of the same degree as F, okay? And what else? So if you wait long enough in the renormalization, each periodic point of the Fielding-Julia set will be expanding, okay? And therefore, actually, you deduce that the Fielding-Julia set and the Julia set actually agree. So there are no interior components to the Fielding-Julia set. And in fact, the map G will be topologically conjugate to a polynomial-like map, topologically only. See, only topologically conjugate, okay? But this is good already to deduce certain things. So in particular, there are no wandering domains because, well, because the polynomial-like mappings don't have wandering domains. And you also deduce that the Julia set is locally connected because it is a theorem for standard polynomial-like maps. If they are infinitely renormalizable about the type on the real line, then there are no, I mean, the Julia set is locally connected. You look at the puzzle pieces, and they shrink to, I mean, 2 points. You know, nested sequence of puzzle pieces, they shrink to points. So that's the main theorem. I just wanted to put the statement right away so we don't miss it. But I need to explain what renormalization means. So I'll just I'll digress here a little bit. I mean, we heard about the definition of renormalization in Pablo's talk already. So I'll do it pretty much, I mean, slightly differently from what he did, but totally equivalently. So I just consider unimodal maps which are symmetric about the origin, you know, on the interval -1, 1, say it's normalized. And so 0 is the critical point. So to be renormalizable means that there is some neighborhood of some little interval containing the critical point, which is symmetric about the critical point, which is mapped around by F, and after some finite number of iterates comes back to itself, into itself, and so that the composition along the cycle gives you a new unimodal map. Okay. Well, I don't. I mean, if it's not symmetric, there's some things you can do, but let's not worry about that. For the sake of this talk, everything is symmetric. Okay. So, so if this number p is the smallest possible, in other words, if the cycle has the smallest possible period, right? Then you define the renormalization, the first renormalization of f, to be this this return map fp, right? It will map this little interval here into itself, and linearly rescale to be back in the interval -1, 1. Okay, so lambda is just this number here. Is the pth iterate of 0. Okay. So this is maybe not too important right now, but the cycle of intervals that you get, if you look at the order of the intervals on the line, it actually determines what is called a unimodal permutation. A unimodal permutation is a permutation of the number 0 up to p-1 that when you graph them, gives you again a unimodal shape. Okay, this is not going to be used here, but anyway, this is because it was I used the slides from some other talk. So anyway, so if the map is renormalized, when you renormalize it, it makes sense to ask, is this new renormalized map itself renormalizable? If it is, you can calculate the second renormalization, and you can keep asking this question, and you calculate the third, the fourth, and so on. So a map is infinitely renormalizable if all of these renormalizations are defined Rn of f for every n, okay? And these are the maps that matter to us. So here's a picture that I like to draw. So here's the interval -1, 1, and this little x here is 0, is the critical point. So you have to imagine that there is a self-map of this interval, which is unimodal, which is f, excuse me, and being renormalizable means that there is some little interval about a 0, which is symmetric, and a bunch of other intervals, which are pairwise disjoint, and the map goes like that, okay? And you come back. So after a finite number of iterates, you come back. Here I've drew a period 4 situation, which could also be actually the second renormalization of a period 2 situation. Okay, so so when you do that and you rescale back to the interval -1, 1, you can now just consider you go around the diagram and you define the renormalization in the way it's written here, right? So it's a self-map of this blue interval. And by the way, I drew it in a way that suggests that this rescaling is orientation preserving, but it's not necessarily. It might be orientation reversing, because when you compose around the cycle, depends on how many times you are on the right or on the left of the critical point. So it might be the case that you get a unimodal map that looks like this rather than like this. So you start with something that is like this, but it may have in the middle, you may have something that looks like this. So you need orientation reversing rescaling. Okay, so here's some notation. Unfortunately, you always need some notation. So if you have an infinitely renormalizable map, as I just defined, the nth renormalization can be written like this. So you start renormalizing, you see that you have higher and higher powers of f, and rescale by factors which are, the lambdas are smaller and smaller and smaller. Okay. The qn's are just the product of the periods of the renormalizations, of the successive renormalizations up to that point. The lambda n's are just the close. They're just given by the closest approaches in the combinatorial sense, the closest approaches to the critical point. Okay. So so these guys, the periods, well, they're called periods, I guess anyway. So these are called periods. And being bounded type means that these periods are bounded from above by some number n, okay? And those are the situations we're going to be dealing with. There is also some more notation. These intervals, the interval containing the critical point at the nth level of renormalization is denoted delta sub 0 n, and the images are therefore delta sub I n, the fi image of delta sub I n. And the I varies from 0 to qn minus 1. So these intervals are called the renormalization intervals at level n, okay? And then, there's some notation about their collection and so on. This is not going to be too important. The important thing here is that when you take these collections of intervals and you look at the union at each level, and then you take the intersections of these unions, what you get is precisely the post-critical set, okay? And the first theorem here is due to Sullivan. It's the real bounds. So the real bounds actually tell you that this post-critical set is a Cantor set of with bounded geometry, okay, in the bounded type case. So bounded geometry means that in the construction of the Cantor set, so at each step there is an interval subdivided in, containing a bunch of intervals from the next level, and bounded type means, bounded combinatorics means, bounded geometry means that the ratio of the parent to each one of its children is bounded from above and below by some constant, and also the gaps are controlled. The gaps are not too narrow, okay? So this is what it means for Cantor set to have bounded geometry, and Sullivan proved that. Hello? What do you mean? The gap? Well, this sort of more or less follows from the fact that there are at least two intervals here, and they are at least as as big as the big one, right? They cannot be too big. Okay. Anyway, so but Sullivan. Oops, sorry. Oh my God, I'm having trouble with this thing here. Sullivan also showed that these bounds. By the way, so this statement here is the bounded geometry statement, but there's some more stuff here. So there are these intervals at level n, and they are kind of permuted by the map. So if you look at two such intervals at the same level, and you look at the map that takes one to the other, except for the one that contains the critical point, you have to exclude that, which is not a diffeo. The others are diffeos, and these diffeos have derivatives which are controlled by the ratio of the corresponding intervals, the source interval and the target interval, with constants that depend only on f. And Sullivan also showed that if you renormalize enough times, then these constants actually become universal. So this is what he calls Bow bounds. Let me just, I was there when Dennis came up with the expression Bow. So there's a little joke here. Bow is a French word, right? So why did he use this word, right? He used this word because he was thinking of the sequence of renormalizations being bounded and eventually universally bounded. So you've seen this picture before, right? So anyway, I drew it a while ago, so so it had everything to do with period doubling. So this is why he used the word bow, Anyway. That's right. Yeah, that's true. Yeah. Right. And in fact, you are actually starting at the wrong place, right? Because the interval that contains the critical point in the period doubling situation is this one here. It's not this one, but anyway, it's okay. So also, so intuitively, or in informal terms, it's better to say the following. Forget all this notation. What the theorem is saying is that the post-critical set is a bounded geometry. The successive renormalizations are uniformly bounded in the C2 topology. I don't know if you noticed this in the statement. I didn't really stress it, but if you go back to the statement, the map has to be C3 here. Sullivan proved a more general real bounds kind of theorem for things which are much below C3, right? But if you assume C3, you actually get that the renormalizations are bounded in the C2 topology, okay? And more generally, if they are CR, you get control in the CR-1 topology. So here it will be, I'm stating it like this because we are going to say something about C2 in a moment. So let's see, how much time? Okay. So the theorem is saying these three things. It's saying that the post-critical set has bounded geometry, the successive renormalizations are uniformly bounded in the C2 topology, and that the bounds become eventually universal, okay? They depend only on the bound of the combinatorics of the map. But Sullivan also showed the complex bounds. So if you have, say, a real analytic map and you start renormalizing it, and a complex extension of it, the complex extension is also renormalizable. This is something that follows from a picture by Doody and Hubbard. And if you keep doing it, you know, these maps become quadratic-like map or polynomial-like map, polynomial-like maps, okay? With good bounds. Good bounds means that, among other things, it means that the annulus determined by, remember there was this u and there was a v, right? So there's v minus u, it's an annulus. So this annulus has to have modulus, it shows that the annulus has modulus bounded from below by some constant. So these are the so-called complex bounds. And the complex bounds are also both. They also become asymptotically universal. But I didn't state it precisely because I'm going to state a more precise theorem in our context. So if you have an asymptotically holomorphic map of order at least 3, so it's at least C3, and you have, and it's such that there is an interval restricted to which the map is unimodal, infinitely renormalizable of bounded type, with the type bounded by n, then you can find a constant that depends on this n and some deep level beyond which the following hold. So there should exist some Jordan domains containing those intervals, delta sub I n, two families, u sub I n and v sub I n, which are like quasi disks. And so these guys contain the corresponding renormalization interval at the level n. They're all, the VINs are pairwise disjoint, sorry, and F maps them like so. Okay, I'll draw a picture so you see what I'm trying to aim at. And what you know is that if you look at the return maps, from each UI sub n, from each U sub IN, from UIN to VIN, these maps are well-defined, asymptotically holomorphic polynomial-like maps, okay? And moreover, they have good bounds. So the bounds of the annuli are, the annuli have moduli bounded from below, and the domains themselves, the codomains, the VINs, are not too big compared to the interval that they contain, okay? And moreover, if you look at this return map, it's an AHPL map, so you can look at its dilatation, and the dilatation actually is vanishing exponentially with n. Okay, so let me draw a picture because, by the way, this theorem is actually just a restatement in a very special case of a much more general theorem due to Trevor Clark, Sebastian, who's right here, and Sofia Trejo. Okay, it's actually part of it is Sofia's thesis. So this is a paper which has already appeared. It's in Communications of Mathematical Physics last year. So let me give an example. So let me assume that n equals 2, that 2 is a big number. For me, 2 is a big number, okay? It's beyond this n0 that I stated in the theorem, yeah? So just for the sake of drawing it. So 2 is a big number, and I'm looking at period doubling situation. So I'm looking at second level, and the q sub 2 is what? It's 2 times 2, it's 4, right? So it's the same picture I had before, but now it's going to be complex. Yeah, sometimes I can do arithmetic, Anyway, I have to deal with this guy here. So, right. So, so remember that there was this little interval containing the critical point, which was going to be mapped around like this. It first goes to this interval here, which contains the critical value. Right here, it folds, and then the remaining maps are diffuse. So the complex bounds are telling you that there's some green domain U. This is U sub 04 in the notation that I introduced before, which is mapped around like so. So this guy goes to U sub 1, 4. Sorry, U sub 1, 2. Not 4, but 2. Then it goes to U sub 2, 2. Then it maps to U sub 3, 2. And then it comes back. And when it comes back over itself. So it becomes this yellow domain here, okay? And you can push this around as well. You can continue. So this yellow guy around the critical value goes to a yellow guy around the critical point. Around the critical value point goes to a guy around the critical value, I'm sorry. Then it goes here, and then you're done. And by the way, this picture is just a schematic. It's not meant to be anything more than that. This interval here, which contains a critical value, is about the order of the square. The length of this interval is like the square of this, or the dth power, where d is the order of a critical point. So it's much smaller. Okay, so this picture is misleading. It's not meant to be something quantitative. It's just qualitative. So these domains are also not so nice, like ellipses, like I drew them. They're usually pretty horrible. And the way the proof goes is actually by taking some guy that, the yellow guy here, this yellow guy here, you find it, and you kind of pull it back. Okay, it's by taking pre-images, not by going forward, but by going backwards. Okay, so the complex bounds are telling you that. Oops, I'm sorry. The complex bounds are telling you that, among other things, that the moduli of these annuli, they're all bounded from below, and that the return maps, if you take any one of these guys and wait until you come back, the return maps are these AHPL-maps with good bounds, with good control, and in fact, the maximum dilatation vanishes exponentially fast with the step of renormalization. So I hope that this explains the contents of that. But we need more than that. So here's the novelty. The first novelty here is C2 bounds for these renormalizations. Now, for Sullivan, for the actual polynomial-like case, these bounds come for free, because if you have a holomorphic map and you bound the C0 norm, right, like the theorem does, like the complex bound do, if you bound the C0 norm, you bound all the other norms, right? So on a slightly smaller domain, you bound all the other norms. So, excuse me. But in our case, the maps are not holomorphic; they are only asymptotically holomorphic. So, you need to actually show that the maps are bounded in the C2 topology. So we have a theorem showing that. Okay. So if you have something which is infinitely renormalizable and is asymptotically holomorphic and polynomial-like already maybe, then the renormalizations are bounded in the C2 topology of the UNs, okay? And moreover, this constant is also Bow. I mean, after a sufficiently large number of renormalizations, the constant becomes universal. So the is the real bounds and the complex bounds, and it also uses the chain rule for the second derivative of a composition. So here's something that I want to write down. So suppose you have two maps in Rn, and you're looking at the composition, and both maps are C2, and you're looking at this composition, and you want to look at the second derivative of this. So what is the second derivative, right? So the derivative is a n by n square matrix, which is made up of the Hessians of the, you juxtapose the Hessians of the components of the map, right? So if you write it in matrix form, the chain rule has a very nice, formula that people don't really seem to use too much. It's essential here. So this is just, let's see. Yes, so this is just a second derivative of f. So this is an n by n square. Oh, hello? Okay. This is funny. Can you hear me? Hello? Okay. So, so it's the second derivative of f calculated at g times, now I have to multiply by a matrix that has to be n square by n square, right? Because I want to get something which is n by n square. So what you do is you multiply by the first derivative of g tensor with itself. Okay? So you take the tensor product or the Kronecker product of the two matrices, plus then here comes the derivative of f calculated at g. Well, this is an n by n matrix. So now in order to get an n by n square, you have to multiply by something which is n by n square, right? So you multiply just by the second derivative of g. Okay? So this formula is crucial in the proof of this theorem because of the shape of the formula. We apply it to the iterates of our map. So there is an induction that you have to use. So if the formula becomes a little bit more complicated, but it matches perfectly with something that you can do about the geometry of the Cantor set. I'm not going to explain here. But the shape of the formula is essential. And if you remember the, for those who work in one-dimensional dynamics, right? So if you remember the formula for the nonlinearity of a composition of two maps, this is pretty much what it is. Imagine you could do something which you cannot do, which is to divide this thing here by, the first derivative of the composition, which would be df calculated at g times dg. If you divide here on both sides, then there is some cancellation, and what you get is that the nonlinearity of the composition is the sum of the nonlinearities of the two maps. I mean, one of them transported by the other. So it's the analog of that, okay? So it's like a cocycle, and it's very important that it has this shape. See, if you look at the second derivative in terms only of components, you go nowhere, okay? Anyway. Okay, so but remember that there was this statement of the main theorem. I'm going to just repeat it here, right? So this is the statement. So I just now want to give you, in the final minutes of my talk, I want to give you some idea of what is, goes into proving the theorem, right? So what are the ingredients? So this is the statement I hope you remember. And it's just saying that sufficient high renormalization of an asymptotically holomorphic map becomes an asymptotically holomorphic polynomial-like map with good bounds, right? And you deduce that, from that you deduce that there are no wandering domains, that the Julia set is locally connected, etc., etc. So we use. So the proof uses, of course, the real bounds, the complex bounds, the C2 bounds that I just stated, which are new. But it also uses the control of a distortion of by f of the hyperbolic metric in the codomain of the map. So the map goes like this, and it's symmetric about the real axis, and you can read the real axis from V, and you get two topological disks, which are hyperbolic Riemann surfaces. They have their own Poincare metric, so you can use the Poincare metric there. And why is that important? So suppose you show that f expands the hyperbolic metric. And suppose that you have a periodic orbit here that stays off the real axis. So let's say period 5. So you start here and you go, maybe you do like that. Maybe you do something differently. But in any way, you come back after a few iterates. If there is expansion of the hyperbolic metric, because the hyperbolic metric here is actually locally comparable to the Euclidean metric, if you go around the cycle a few more times, you actually get expansion in the Euclidean metric. So you deduce that the eigenvalue of the periodic orbit is really greater than 1. So the orbit is expanding. So this is proving that one of the statements in the theorem that all periodic orbits in the field in Julia set are expanding. What about the ones which are sitting on the real axis? Those you don't have to worry about, because a sufficiently deep renormalization of a C3 map will actually always have negative Schwarzian. And for negative Schwarzian maps, you cannot have attracting cycles if the critical point is recurrent, right? So you don't have to worry about that. So another thing we do in the proof is we control the size of puzzle pieces. I'm not going to go explaining this, but the notion of puzzle pieces go back to Yoko's. And if you have nested sequences of puzzle pieces and you show that they shrink to points, this actually shows that the Julia set is locally connected. So you use the expansion of the hyperbolic metric to show that the puzzle pieces can contract, they shrink, okay? Well, you have to build puzzle pieces. We do that in the paper. Yeah, I'm not explaining how it's done either. Yeah, that's a kind of a, sort of subtle construction, but it can be done. And in the middle of this, we need to prove some things and we need to use things like holomorphic motions. In particular, we have to use something called Slodkowski's theorem. So here, the key to the proof is this expansion of the hyperbolic metric. So here's a statement. So if you have such a map and you take a point in the field in Julia set, whose orbit never lands on the axis, so you iterate forever, you never land on the real axis, then if you look at the successive iterates of f, and you look at any tangent vector at that point, its hyperbolic length is really increased by the iterates of f, okay, by the derivative. So this thing goes to infinity. And the idea behind the proof is the following. You look at this Stoilov decomposition, and G is conformal, I mean it's holomorphic, and phi is quasi-conformal. And you're going to use the fact that, well, number one, holomorphic mapping a domain U onto the domain V, which is larger, will actually expand the hyperbolic metric of the larger domain, okay? This is just a version of the Schwarz lemma, really. But I'll give you the precise statement in the next slide. And phi is quasi-conformal, so it's a quasi-conformal diffeomorphism, so it might expand or it might contract the hyperbolic length of tangent vectors. Yes? I'm just using the hyperbolic metric on V minus the real axis. So it has two components. It has this top part and the bottom part. So it's hyperbolic metric there. Yes? Okay. Yeah, you have to remember that these when you remove the real axis on the complement, the map has globally defined inverse branches on those domains. Okay? So you know, okay. So now the point is that this map phi is quasi-conformal, so in principle it could contract the hyperbolic length. But here is the principle that because the dilatation of phi is small, if you have a 1 plus epsilon QC map, so if it's an almost conformal, then there is a lemma that we prove that an almost conformal map, which is at least C2, it has to be at least C2 for this to hold, is an almost isometry in the Poincare metric. There's a very quantitative way in which this is true, and I'm going to state that. So if you can do these two things, you can show this fact, and from this fact you can prove the main theorem. Okay? Well, I mean, quite a lot of work, but anyway. So how do you bound expansion? So we use a lemma due to McMullen, really, which is the following. I mean, it's not. He never wrote this expression explicitly. He gives something implicit in his book, but if you work it out, you get this. So if you have, suppose you have two hyperbolic Riemann surfaces, one containing the other, and you have a holomorphic map from the smaller one onto the big one, okay? And suppose it's holomorphic, univalent, so it's univalent. Then if you take a point in X and any tangent vector at that point, then the derivative of G calculated at that vector, the hyperbolic length in Y, in the target, of this vector is greater than or equal to some number times the hyperbolic length of V in X, in the source. What is this number? This number is given by some universal function, here's the universal function, of the hyperbolic distance between X and the complement of Y. So just to, yeah, I hope it's okay. So just to give you an idea, suppose the situation is like this, you have, here's Y, and suppose X is like this. So if you're here, see a point here is very far from the boundary of X in Y. So this hyperbolic distance is huge. So what happens here? If the hyperbolic distance is huge, this number is practically 0. So log of 1 is 0, but sine of S is going to infinity. And these two things, they fight with each other, and the limit is 1. So this means that the distortion, I mean, the map is actually becoming like an isometry near that part of the boundary of X, if you're here. But if you're here, if you're very close, then there is a huge expansion. There's quite a lot of expansion. So anyway, so this is what controls the expansion by the holomorphic part, right? Okay, this is just for one iterate of the map, but then you have to work things out when you iterate the map, right? And when you iterate, the factors are intermingled. You first do a G, then you do a phi, then you do a G, then you do a phi, and so it's a little bit more complicated than that, but just to give you the general idea. So how do you bound the, so the lemma is essentially due to Mach, and this universal function is continuous, it vanishes at 0, and it goes to 1 as the parameter S goes to infinity. So it's a universal function right here. Well, no, I'm not saying bounds are sharp, okay? It works, and it has to do with, comparing like the hyperbolic metric in the punctured. Yeah, I mean, we don't need that, yeah. Okay, but it comes from comparing the hyperbolic metric, say, in a disk versus the hyperbolic metric in the punctured disk, okay? It has to do with that, so anyway. I have like one minute or something. I can wrap it up in 1 minute, I think. So to bound the contraction, you use the fact that the possible contraction. You need to bound the possible contraction of vectors by phi from below. So first you use this fact here, this general fact about quasi-conformal diffeomorphisms. This is like an isoperimetric inequality. This is well-known stuff that you find in almost any book and in QC maps. But here I'm using the hyperbolic metric, not the Euclidean metric as it usually presented, but it's the same thing really, because you can use any conformal metric that you use is going to work here, okay? So you don't need that. I mean, sorry, you need that, but I'm saying you don't need to worry about the fact that I put here the hyperbolic metric. So what is this J sub phi h here? This is the hyperbolic Jacobian of phi. Is the Jacobian of phi measured in the hyperbolic metric of the domain. So remember that phi is a self-map of y. It's a self-map of v, and it preserves the real axis. So if you remove the real axis, it's a self-map of y. And I'm saying that, so in order to bound this expansion or contraction, either expansion or contraction of the hyperbolic metric of this vector v, it suffices to bound the Jacobian, because this k here is actually approaching 1 as you renormalize, okay? So with this you have this proposition. So the proposition, I'm going to ignore these technicalities here, but essentially it's saying that if phi is a C2 quasi-conformal diffeomorphism of the disk, and it's asymptotically holomorphic near the boundary of the disk with a certain rate, then you can bound the Jacobian, the hyperbolic Jacobian, in terms of that rate. You just lose a little bit, okay? And this is proved by the disk, but then you can actually do it in any simply connected domain, or you can even kind of quotient it down to hyperbolic Riemann surfaces. So in fact, this lemma, this proposition, potentially has applications in other things like problems in conformal Riemann surface theory and so on. So I don't know. So in the application, the beta that appears here is the R minus 1, is the degree of differentiability minus 1. And here's some references for you, okay? This paper here has already appeared, as you see. This is still, it's out in the archive, but it's submitted. And this is the paper that I mentioned with Wellington and Alberto. And this paper is coming from Pablo's thesis, okay? And he has now a nice continuation in Duke, which is even better. Anyway, thank you. Thanks.
Is it only,
I think you missed it. There was a slide saying that the motivation is to study these maps in order to try to prove hyperbolicity of renormalization in the CR case without using all those fancy functional analytic techniques that we used with Wellington and Alberto. So it's kind of to redo the theory in a way that becomes more unified with what McMullen, Sullivan, Avila, Liubich, and so on did, okay? So it becomes more, aligned in nature with these holomorphic or quasi-conformal techniques. Yeah, I mean, by the way, there is a, I should say right away, I'm assuming that the maps are C3 plus something, but in my paper with Wellington and Alberto, we only need C2 plus, a number which is like the highest Hausdorff dimension of the maps and the attractor of the renormalization, okay? So we go below C3. Here we need to be above C3 because of the techniques we're using.